Welcome, everyone. My name is Christopher Kuhn. I am researching failure prediction in autonomous driving at both Technical University of Munich and the BMW Group. In this video, I will introduce you to our approach to introspective black box failure prediction for autonomous driving. Despite recent progress in the field of autonomous driving, failures are still inevitable. Such failures can be due to complex traffic, unforeseen edge cases, or perception failures. It is not always possible for an autonomous car to resolve such a situation alone. It is, however, possible to predict that such a situation will arise. This way, there can be enough time to take appropriate countermeasures, such as giving a remote human operator control before a failure actually occurs. For this, early failure prediction is required. In this work, we present our approach to predicting failures of an autonomous car up to 7 seconds in advance. Our idea is based on recording driving data and then using both successful and failed scenarios to train a dedicated failure prediction model. First, let's look at existing works in this area. There are only few existing papers for failure prediction in autonomous driving. The approaches that do exist are generally based on using some form of disagreement between models to infer failure. In those papers, an end-to-end steering angle prediction network is used as a proxy for an actual autonomous car. The first paper shown here monitors the disagreement between such an end-to-end model and the output of the Tesla autopilot system. This allows to predict disengagements of the Tesla autopilot up to 5 seconds in advance. Another approach trains a dedicated failure prediction model with video sequences ending in a large disagreement between human ground truth driving data and, again, an end-to-end driving network, which allows them to predict a disagreement 2 seconds in advance. Finally, an important concept we use in our approach is introspection. In the paper introducing introspection, failures of an autonomous drone are recorded and used as training data to be able to predict future failures of the drone. In our work, we use this idea as an inspiration to perform failure prediction for autonomous driving, without requiring any ground truth human driving data or a second model to compare to. Here we first show an overview of the proposed approach. Our approach is based on predicting the failures of an autonomous car by treating the car itself as a black box. We only use state data to infer what the car is doing. As failures, we consider disengagements of the autonomous mode of an autonomous car, at which point the car cannot drive on its own anymore and would likely crash without intervention. We use the sequence leading up to such a disengagement as data, and we give it the label failure. We also sample an equal amount of sequences from the much larger portion of driving where the car drives successfully to obtain a balanced data set. This allows us to then train an LSTM classifier that classifies the current sequence as either success or failure. We additionally use a moving average filter to remove outlier predictions. So the general idea is to train a classifier to distinguish between failure and success based on state data. Next, let's look at the specifics of how we approached this task. For both failure and success sequences, we use sequences of 10 seconds of driving. It is possible to use more than 10 seconds. However, in practice, the environment starts to be very different to the moment of failure if we go back more than 10 seconds. We only use state data, meaning speed, the angle, acceleration, angular speed, and also the number of detected objects as a simple, straightforward measure of scene complexity. We sample those features at a frequency of 10 Hz. This results in 100 feature state vectors per sequence. We then split those 100 state vectors into shorter overlapping training samples, for example at a length of just 3 seconds. Then we train a straightforward LSTM network to classify each 3-second sample as either success or failure. This way, the network does not have to observe the entire 10 seconds leading up to a failure, but can already detect failures after observing just 3 seconds, allowing it to predict failures up to 7 seconds in advance. A key component of our approach is to have actual driving data in autonomous mode that contains failures. No large-scale dataset containing failures of autonomous cars are currently publicly available. We cooperated with the BMW Group to obtain several months of driving data of their research vehicles driving in their autonomous mode on public roads. We extracted all disengagements out of this data. Each disengagement is either caused by the car requesting human takeover or by the human safety driver intervening. This way, we obtain a total of 1,032 unique disengagements. We additionally sample the same number of 10-second sequences from undisrupted successful driving, resulting in a balanced dataset of almost 6 hours of actual autonomous driving on public roads. From each 10-second sequence, we take 100 sensor readings at a frequency of 10 Hz. And here we show again the features that we use, namely speed, frontal acceleration, lateral acceleration, steering angle, angular speed, number of detected objects. We divide the sequences into shorter training samples and then use those samples to train an LSTM classifier. After training the classifier with 90% of our data, we now look at the results on the 10% of the data reserved for testing. First, we evaluate our failure prediction model using the receiver operating characteristic curve. To the left, we show the area under the ROC curve for straightforward comparison of different models. We evaluated different training sample lengths ranging from 1 second to 5 seconds. We also investigated the impact of applying a moving average filter to the output of the LSTM. The classification results were consistently better than filtering the predictions. Interestingly, the best results were obtained when using a medium training length of 3 seconds, meaning the model observes 3 seconds of state data before making a decision. Using a shorter time results in the model learning mostly short-term temporal features, while learning from 5-second samples means the model starts to look for long-term features. To the right, we also show the entire ROC curve for the best setting of 3-second training length samples and applying the output filter. We can see that averaged over all time points, the disengagement prediction can, for example, achieve a false positive rate of 0.2 at a true positive rate of over 85%. Next, we focus on the temporal component of the proposed approach. So, how does the introspective model fare regarding early failure prediction? Here, we show the prediction error for both test sequences ending in a disengagement and for sequences from successful driving. We chose a threshold setting that favored a higher true positive rate while accepting a higher false positive rate, since false positives are less safety critical than false negatives in failure prediction. The error in failure sequences clearly decreases when getting closer to the point of failure. 7 seconds in advance, The error is at almost 15%, but declines to less than 10% directly before the disengagement. This low error for failure sequences, even 7 seconds in advance, comes at a false positive rate of less than 1/3. Now let's summarize the results of this paper. Regarding the failure prediction performance, our approach achieved a prediction accuracy of 82% averaged over all time points. 7 seconds in advance, a true positive rate of 85% can be achieved when accepting 31% false alarms. This way, the proposed approach achieves accurate failure prediction multiple seconds earlier than related works. Another relevant property is our black box assumption. No assumptions on the underlying system are made, meaning it can be applied to any kind of autonomous system. Only commonly available measurements, such as the state data and some form of object detection for the number of detected objects, are required. The main requirement is to have observed enough failure data to learn from. In fields such as autonomous driving, such data becomes available as a side product of the extensive test drives that are commonly done anyway. Using disengagements from recorded test drives as training data effectively allows to obtain labeled data for free, while also allowing to achieve highly accurate failure prediction many seconds in advance. For future work, a straightforward step is to add images as another sensor modality. It would also be interesting to combine this black box method with confidence measures from the system itself. This could allow to combine the strength of existing methods with the benefits of introspective black box failure prediction for autonomous driving. Thank you very much for taking the time to watch this video about our research results regarding failure prediction. If you have any comments, feedback, or ideas, we would love to hear from you, so feel free to get in touch.